Imagine for a moment the night sky, a vast and silent ocean pricked with the light of 1,000,000,000,000 distant suns. For all of human history, we looked to this celestial expanse and believed that what we could see was, more or less, all there was. The stars, the galaxies, the shimmering clouds of gas and dust. These were the building blocks of the universe, the grand cosmic architecture. And yet, this magnificent view is a profound illusion, a beautiful but misleading sliver of a much deeper reality. Every star, every galaxy, every wisp of glowing nebula that our most powerful telescopes can detect, along with every planet, every mountain, and every living being, together make up a mere 5% of the known universe. The rest, the overwhelming 95% majority, is hidden from us, dwelling in the dark. This is the story of that darkness, a century-long scientific detective story to uncover the nature of the universe's missing mass, a substance astronomers call dark matter. It's a story I'm thrilled to share with you. And I'd love to know where you are on our own small planet as this story begins. So please feel free to comment with your location and what time it is where you are. And to ensure you are notified when we explore other great scientific stories, please subscribe. Our quest to understand this invisible universe did not begin in a flash of insight, but with a quiet, persistent puzzle noticed in the elegant, clockwork dance of the stars themselves. A subtle anomaly in the familiar starlight of our own galactic home. And that home, our Milky Way galaxy, was in the first years of the 20th century a frontier of both human knowledge and profound misunderstanding. The prevailing picture of the cosmos was small, comfortable, and centered on us. It was in this era that a Dutch astronomer named Jacobus Kapteyn embarked on a project of almost unimaginable ambition: to create the first comprehensive map of our stellar island. Kapteyn was a man defined by meticulous patience, a celestial bookkeeper for the heavens. Working from the University of Groningen, he understood that he could not possibly photograph and catalog every star himself. Instead, he devised a brilliant collaborative program, coordinating with observatories across the globe to create a systematic stellar census. He divided the entire sky into 206 regions, which he called his selected areas. And for decades, photographic plates arrived at his laboratory in the Netherlands. There, Kapteyn and his team would spend countless hours hunched over illuminated tables, measuring the faint positions of stars with painstaking precision, comparing plates taken years apart. They were looking for tiny, almost imperceptible shifts. One of these was parallax, the slight wobble in a star's apparent position caused by the Earth's own orbit around the Sun, a triangulation method that yielded the star's distance from us. The other was proper motion, the star's gradual drift across the canvas of the night sky. By combining these measurements with observations of a star's radial velocity, the speed at which it was moving towards or away from us, revealed by the subtle stretching or compressing of its light waves, Kapteyn could build a three-dimensional model of the galaxy's structure and dynamics. Over years of this heroic effort, a picture emerged, his great life's work published in 1922. The Kapteyn Universe. It was a model of the Milky Way as a flattened, lens-shaped island of stars, perhaps 10 kiloparsecs, or about 33,000 light-years, in diameter, and maybe 2 kiloparsecs, or 6,500 light-years, thick. In this model, our sun sat, quite mistakenly, very close to the galactic center. It was a monumental achievement, the first data-driven map of our galaxy. Yet it was flawed. Kapteyn had failed to account for the pervasive interstellar dust that drifts between the stars, a cosmic fog that absorbs starlight and makes distant objects appear fainter, and therefore closer than they truly are. His universe was far too small, and our position in it was far from central. But buried within his painstaking calculations was the first true hint of the great mystery. Kapteyn wasn't just mapping the stars. He was studying their movements to understand the gravitational engine that drove them. He paid special attention to the way stars bobbed up and down, oscillating through the dense central plane of the galaxy. Just as the speed of a pendulum's swing reveals the strength of Earth's gravity, the speed of these stellar oscillations revealed the strength of the galaxy's gravitational pull in that region. From this, he could calculate the total mass density required to keep those stars tethered. And when he did the celestial arithmetic, he found a quiet but persistent discrepancy. The amount of gravity required to explain the stars' motions was more than the amount of gravity that could be accounted for by the stars themselves. To hold on to its stars, the galaxy needed to be about twice as massive as it appeared. Kapteyn speculated about this missing mass, wondering if it could be hidden in faint dwarf stars, the gaseous remnants of dead suns, or clouds of non-luminous gas. The evidence was tentative. The uncertainties in his data were large, and his model of the galaxy was soon to be proven wrong in its scale. The clue, though real, was dismissed as a statistical ghost, a product of imperfect data. At around the same time, a brilliant British mathematician and physicist, Sir James Jeans, approached the problem from a different angle. While Kapteyn was the master of observation, Jeans was a titan of theory, a man who saw the universe as a grand set of physical principles waiting to be solved. He was renowned for his work on the behavior of gases, and he applied the same kind of statistical mechanics to the grand, swirling collection of stars that made up the Milky Way. In his analyses, Jeans independently confirmed Kapteyn's strange finding. He calculated that for a stellar system like ours to remain stable, for it to not fly apart or collapse in on itself. There had to be a certain relationship between the kinetic energy of the stars, their motion, and the gravitational potential energy holding them together. When he applied his rigorous mathematical framework, known as the Jeans theorem, to the observed stellar velocities, he too arrived at the conclusion that there was more gravitational influence at play than could be seen. He even gave a name to the potential source of this gravity, musing in his writings about the possibility of dark stars or other non-luminous matter populating the galaxy. But like Captain's, his work was met with polite academic interest rather than revolutionary fervor. Astronomy was in a state of profound flux. The very year after Captain published his model, Edwin Hubble would prove that the Andromeda Nebula was not a gas cloud within our own galaxy, but a colossal island of stars in its own right, millions of light years away. The universe had suddenly become incomprehensibly vast, and our place in it vanishingly small. In the midst of these paradigm-shattering discoveries, the subtle mathematical oddity of a few fast-moving stars in our own backyard seemed like a secondary concern. The error bars on these early measurements were enormous, and it was widely assumed that with better observations and a clearer understanding of stellar populations, the discrepancy would simply melt away. Perhaps there were just more faint, brown dwarf stars than anyone had accounted for. Or maybe the complex effects of interstellar absorption were skewing the results in ways no one yet understood. The anomaly was a whisper in a thunderstorm of cosmic revelation. It was a loose thread in the tapestry of the heavens that most astronomers chose to ignore, assuming it would eventually be tucked neatly back into place. They could not have known that this single, stubborn thread, when pulled, would unravel nearly everything they thought they knew about the fabric of the cosmos. For the moment, the mystery lay dormant, a footnote in the annals of galactic astronomy, waiting for a more powerful set of eyes to look far beyond our own local neighborhood and into the deep, intergalactic darkness, where the universe's missing mass would finally begin to scream its existence. The quiet puzzle of stellar motions had planted a seed of doubt, but the true revolution required a mind bold enough, and perhaps eccentric enough, to see not just a statistical error, but a fundamental challenge to the laws of the universe. That bold and eccentric mind belonged to a man named Fritz Zwicky, a brilliant and notoriously abrasive Bulgarian-born astronomer who, after being educated in Switzerland, made his home at the California Institute of Technology. Zwicky was a force of nature, a fountain of radical ideas, many of which would later be proven spectacularly correct. He was the first to propose that supernovae were the explosive deaths of massive stars, leaving behind a hyperdense core he and his colleague Walter Baade called a neutron star. He was a pioneer in the concept of gravitational lensing, the bending of light by massive objects. He was a true visionary, but his genius was matched only by his cantankerous and combative personality. He famously referred to his colleagues at Caltech as spherical bastards because, he explained, they were bastards no matter which way you looked at them. He was a lone wolf, an intellectual maverick who trusted his own calculations above all else. And it was this unshakable self-confidence that led him to make the most audacious claim of his career. In the year 1933, Zwicky turned his attention and the formidable power of the 100-inch Hooker telescope at Mount Wilson Observatory towards a distant, glittering metropolis of galaxies known as the Coma Cluster. Located in the constellation of Coma Berenices, or Berenice's Hair, this cluster is a majestic and ancient swarm of over 1,000 galaxies, all bound together by their mutual gravity. It lies at a staggering distance, roughly 98 million parsecs, which is about 321 million light-years from Earth. To the naked eye, it is completely invisible, but through a powerful telescope, it appears as a collection of faint, fuzzy smudges of light, a celestial beehive of unimaginable scale. Zwicky was not interested in simply photographing this cosmic city. He wanted to understand its dynamics, to take its pulse. Using a spectrograph, an instrument that splits light into its constituent colors like a prism, he meticulously measured the speeds of several individual galaxies within the cluster. He was using the Doppler effect, the same principle that makes an ambulance siren change pitch as it passes by. Light from a galaxy moving away from us is stretched to longer, redder wavelengths, a phenomenon called redshift. The faster the galaxy is receding, the greater its redshift. By measuring these tiny shifts in the spectral lines of the galaxies, Zwicky could determine their line-of-sight velocities relative to the cluster's center. What he found was nothing short of astonishing. The galaxies were moving at colossal speeds. Some were whipping through the cluster at more than 2,000 kilometers per second, which is over 4.5 million miles per hour. This was a cosmic hurricane, a swarm of galaxies moving with a kinetic energy that was simply breathtaking. For Zwicky, these incredible velocities posed a fundamental problem. He knew that for a system like a galaxy cluster to be stable, it had to be held together by gravity. There had to be a cosmic balancing act, governed by a principle known as the virial theorem. This theorem provides a direct relationship between the kinetic energy of a system, the energy of its internal motion, and its gravitational potential energy, which is determined by its total mass. The faster the galaxies were moving, the more total mass the cluster had to contain in order to generate enough gravitational pull to prevent them from flying off into the void of intergalactic space. Without sufficient gravity, this majestic cluster would have dispersed billions of years ago. It would be like a merry-go-round spinning so fast that all the riders are flung off. So Zwicky performed the calculation. He used the observed velocities to determine the cluster's total kinetic energy. Then, using the virial theorem, he calculated the gravitational potential energy, and therefore the total mass required to keep the system in equilibrium. The result was a number so large it seemed impossible. Next, he calculated the cluster's visible mass. He did this by estimating the mass of an average galaxy based on its brightness and multiplying that by the total number of galaxies he could count in the cluster. It was a rough estimate, but it was the best anyone could do at the time. When he compared the two numbers, the mass required by gravity and the mass provided by the visible stars, he found a shocking, gaping chasm. The gravitational mass was, by his conservative estimate, at least 400 times greater than the luminous mass. There was a colossal amount of matter present in the coma cluster that was generating gravity, but was emitting no light. It was there, but it was invisible. In his 1933 paper, Zwicky laid out his findings with characteristic bluntness. He wrote that this discrepancy is of the order of a factor of 100. If this is confirmed, we would get the surprising result that dark matter is present in much greater amount than luminous matter. He called this unseen substance dunkel Materia, the German for dark matter. He had not just rediscovered the subtle anomaly hinted at by Captain and Jeans in our own stellar neighborhood. He had found it screaming from the depths of intergalactic space, magnified hundreds of times over. The scientific community's reaction was, for the most part, a collective shrug. Zwicky's conclusion was so radical, so contrary to the established picture of the universe, that it was far easier to assume he had simply made a mistake. His abrasive personality certainly did not help his cause. He had alienated so many of his peers that they were disinclined to take his more outlandish ideas seriously. Critics pointed to the enormous uncertainties in his measurements. The distance to the coma cluster, for instance, was still a subject of fierce debate, and the method of estimating galactic mass based on luminosity was fraught with potential errors. For decades, Zwicky's discovery was treated as a peculiar curiosity, a footnote in the study of galaxy clusters, rather than the revolutionary breakthrough it truly was. He remained unperturbed, utterly convinced of his own correctness, and would champion the idea for the rest of his life. But for the mystery to truly take hold of the scientific world, the evidence would need to be reborn, found not in the chaotic swarm of a distant cluster, but in the graceful, orderly rotation of our own galactic neighbors, a discovery that would require a new generation of technology and the persistent, meticulous work of an astronomer who would change our picture of the universe forever. That astronomer was Vera Rubin, and her work in the 1960s and 1970s would transform the dark matter mystery from a fringe curiosity into a central pillar of modern cosmology. Rubin was a tenacious and deeply insightful scientist. a woman who had fought her way into the male-dominated world of astronomy through sheer talent and perseverance. From a young age, she was captivated by the stars, and as a graduate student, she had already begun to explore the large-scale motions of galaxies, finding hints that they were not distributed randomly across the heavens, but were instead clumped together in great cosmic structures, an idea that was, at the time, highly controversial. Her early work was met with skepticism, but it instilled in her a deep-seated belief in the importance of following the data, no matter how strange or inconvenient the conclusions. In the mid-1960s, she began a fruitful collaboration with the instrument maker Kent Ford. Ford had developed a new and exceptionally sensitive image tube spectrograph, a technological marvel that could amplify faint starlight by a factor of 10 or more. This meant that for the first time, astronomers could obtain detailed spectra from objects that had previously been too dim to study effectively, like the faint, glowing clouds of ionized hydrogen gas that dotted the outer edges of spiral galaxies. With this powerful new tool in hand, Rubin and Ford set out to investigate the seemingly simple question of how galaxies rotate. Their first major target was the Great Andromeda Galaxy, also known as Messier 31, a majestic spiral, much like our own Milky Way. Andromeda is our closest large galactic neighbor, lying about 2.5 million light-years away. It is so large that its light has been traveling towards us since the dawn of humanity. To an astronomer, a spiral galaxy like Andromeda is a celestial laboratory for studying the laws of gravity. At its center is a bright, dense bulge where most of the stars, and therefore most of the visible mass, are concentrated. From this nucleus, elegant spiral arms trail outwards, filled with stars, gas, and dust. The laws of gravity, as laid down by Isaac Newton and refined by Albert Einstein, made a very clear prediction about how such a system should behave. Just as the planets in our solar system orbit the Sun, with the inner planets, like Mercury, moving much faster than the distant, ponderous orbits of Neptune, so too should the stars in a galaxy orbit its massive center. The stars near the bright, central bulge should be moving at high speeds, whipped around by the intense gravitational pull. But as you moved further out from the center, into the sparser, dimmer regions of the galactic disk, the orbital speeds should decrease. The gravitational grip of the visible matter should weaken with distance, and the rotation should slow down. If you were to plot this on a graph, with distance from the center on one axis and orbital speed on the other, you would expect to see a line that rises quickly and then falls off sharply. This is known as a Keplerian decline, and it is the signature of a system where the mass is concentrated at the center. This was what everyone expected to find. Rubin and Ford began their painstaking work, pointing the Kitt Peak National Observatory's 84-inch, or 2.1 meter, telescope towards Andromeda. They didn't just look at the center. They systematically measured the speeds of objects all the way along its vast, sprawling disk. They focused on the rosy pink H2 regions, great clouds of glowing hydrogen gas where new stars are being born, because their light contains very specific, sharp emission lines that make for excellent speed markers. Night after night, they captured the faint light, with Ford's spectrograph revealing the subtle Doppler shifts that betrayed the motion of the gas clouds. When they developed their data and drew the rotation curve, it looked nothing like the prediction. In the inner regions of Andromeda, things behaved as expected. The speeds rose rapidly from the center. But then, where the curve should have peaked and begun its elegant Keplerian fall, it did something utterly bizarre. It went flat. The gas clouds in the far, faint, outer reaches of the galaxy were orbiting at the same blistering speed as the stars much closer in, a velocity of roughly 200 kilometers per second, which is nearly 500,000 miles per hour. It was as if you were watching a game of Crack the Whip, and the person at the very end of the line was moving just as fast as the person closest to the center, a physical impossibility without some invisible connection. The result was so strange, so contrary to decades of physical theory, that their first instinct was that it had to be a mistake. They checked their equipment, they recalibrated their measurements, they reanalyzed their data. But the flat rotation curve remained. It was a stubborn, undeniable fact. Perhaps, they reasoned, Andromeda was simply an anomaly, a cosmic freak. So they expanded their search. Over the next several years, Rubin, Ford, and their colleagues embarked on a systematic survey, measuring the rotation curves for dozens of other spiral galaxies. They looked at big galaxies and small galaxies, tightly wound spirals, and those with loose, open arms. And everywhere they looked, they found the same thing. From NGC 4565 to UGC 2885, each galaxy told the same impossible story. The stars at their edges were moving far too fast. The rotation curves were all flat. There was no escaping the conclusion. For these stars to be moving at such high speeds without being flung off into intergalactic space, there had to be an enormous amount of unseen mass providing the necessary gravitational glue. This matter couldn't be in the disk, because they could see the disk, and there simply wasn't enough luminous material there. The missing mass had to be located in a spherical halo, an invisible sphere of substance that surrounded the entire visible galaxy, extending far beyond the faintest, most distant stars. And this halo had to be immense. The calculations showed that for the rotation curves to be flat, this dark matter had to account for as much as 90% of the galaxy's total mass. Vera Rubin's meticulous, undeniable observations had brought Fritz Zwicky's forgotten Dunkel Materie roaring back to the forefront of astrophysics. Where Zwicky had seen the problem on the colossal scale of galaxy clusters, Rubin had found it in the detailed mechanics of individual galaxies. Her evidence was more precise, her methods more difficult to dispute. This was no longer a statistical oddity in a single chaotic cluster. It was a fundamental property of the majestic, spinning disks that are the basic building blocks of the visible universe. The scientific community could no longer ignore the problem. The quiet whisper of missing mass that Captain had first heard in the bobbing of nearby stars had become a deafening shout. The evidence was now staring them in the face from every direction, demanding an explanation. The universe was not what it seemed. It was dominated by a substance that no one could see, no one understood, and no one had yet detected. The hunt was on, and to find more clues, astronomers would next look beyond the galaxies themselves to the most ancient light in the universe, the faint, lingering echo of creation itself. This ancient light, the faint, lingering echo of creation itself, is known to science as the cosmic microwave background, and its discovery is one of the greatest testaments to both human ingenuity and sheer serendipity. To understand it, we must journey back in time, not just centuries, but back to the very infancy of the universe. For the first 380,000 years after the Big Bang, the cosmos was an utterly alien place, a seething, incandescent fog. It was a plasma of unimaginable temperature and density, a chaotic soup of fundamental particles, protons, neutrons, and electrons, all locked in a furious dance with an equally intense bath of photons, or particles of light. In this primordial state, the universe was completely opaque. The photons were trapped, unable to travel any significant distance before crashing into a charged particle, being absorbed and re-emitted in a random direction. Light was a prisoner, and the cosmos was a glowing, featureless wall of white-hot fog. But as the universe expanded, it also cooled. And when the temperature dropped to about 3,000 Kelvin, a little over 2,700 degrees Celsius, or 4,900 degrees Fahrenheit, a momentous transition occurred. At this point, it was finally cool enough for the free-wheeling electrons to be captured by the protons, forming the first stable, electrically neutral atoms of hydrogen and helium. This event is known as recombination, and with it, the universe suddenly became transparent. The photons, which had been bouncing aimlessly through the plasma soup for millennia, were now liberated. With no free charges left to interact with, they were free to stream unimpeded across the cosmos, carrying with them a final snapshot of the universe as it was at that instant of liberation. This flash of ancient light, released everywhere at once, has been traveling through the expanding universe ever since. Over the intervening 13.8 billion years, the relentless expansion of space has stretched the wavelengths of this primordial light, cooling it from its original fiery glow into the faint, cold radiation we detect today in the microwave portion of the spectrum. In the mid-1960s, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in Holmdel, New Jersey, with a large, horn-shaped antenna originally designed for satellite communication. They were trying to create a pristine map of the radio signals from the Milky Way, and to do so, they needed to eliminate every possible source of background noise. But they were haunted by a persistent, faint, and unidentifiable hiss, a low hum that seemed to come from every direction in the sky, day and night. No matter where they pointed their antenna, they checked their electronics, they recalibrated their instruments, they even climbed into the great horn and cleaned out what they delicately referred to as a white dielectric material, pigeon droppings, thinking it might be the source of the interference. But the hiss remained, a uniform, unchanging whisper from the cosmos. Unbeknownst to them, just 48 kilometers away, or about 30 miles, at Princeton University, a team of physicists led by Robert Dicke was actively building an experiment to search for the very thing they had stumbled upon, the thermal afterglow of the Big Bang. When a mutual colleague connected the two groups, the true nature of the hiss was immediately understood. Penzias and Wilson had accidentally discovered the oldest light in the universe. This cosmic microwave background, or CMB, appeared at first to be almost perfectly uniform. A constant temperature of 2.725 Kelvin, or approximately minus 270 degrees Celsius, which is about minus 455 degrees Fahrenheit. This uniformity was powerful evidence for the Big Bang, but the real treasure for understanding the universe's structure, including the role of dark matter, lay in finding the tiny imperfections, the minuscule variations from one spot in the sky to another. The task of finding these variations fell to a series of increasingly sophisticated space-based observatories, beginning with NASA's Cosmic Background Explorer satellite, or COBE, launched in 1989. After years of scanning the heavens, COBE produced a map of the microwave sky that revealed what its lead scientist, George Smoot, described as wrinkles in time. These were incredibly faint temperature fluctuations, tiny hot and cold spots differing by only 1 part in 100,000. They were the seeds of creation, the primordial lumps from which all future cosmic structures, galaxies, clusters, and superclusters would eventually grow. But the very existence and pattern of these wrinkles provided the most compelling evidence for dark matter yet. In the early universe, two colossal forces were locked in a cosmic tug of war. On one side was gravity, pulling matter together, seeking to amplify any region that was even slightly denser than its surroundings. On the other side was radiation pressure, the outward force exerted by the energetic photons, which sought to smooth everything out. Ordinary matter, the stuff of atoms, which physicists call baryonic matter, was caught in the middle. Because it interacts with light, it was buffeted by the radiation pressure. When gravity pulled a clump of ordinary matter together, the density and temperature of the trapped photons would increase, pushing back and causing the clump to expand. This created titanic waves of pressure and rarefaction that rippled through the primordial plasma, known as baryonic acoustic oscillations. Dark matter, however, played by different rules. By its very nature, it does not interact with light. It is immune to radiation pressure. So, while the ordinary matter was sloshing back and forth, the dark matter could respond to the pure, undiluted call of gravity. Long before recombination, vast clumps of dark matter began to form, creating deep gravitational wells, a kind of invisible cosmic scaffolding into which the ordinary matter would later fall. When the universe finally became transparent and the CMB was released, this underlying dark matter structure left its indelible fingerprint on the light. Photons escaping from a region that was dense and compressed appeared slightly hotter, while those from a rarefied region appeared slightly cooler. Crucially, any photon that had to climb out of one of the deep gravitational wells carved by a pre-existing dark matter clump would lose a bit of energy, a process called gravitational redshift, making it appear even colder. By the early 2000s, subsequent missions like the Wilkinson Microwave Anisotropy Probe, or WNMAP, and later the European Space Agency's Planck satellite, had mapped these temperature fluctuations with exquisite precision. The resulting maps looked like abstract, modeled paintings of blue and red, representing the cold and hot spots. By analyzing the statistical properties of this pattern, most importantly, the characteristic size of the spots, cosmologists could create a definitive recipe for the universe. The specific pattern of the fluctuations, the relative prominence of spots of different sizes, was incredibly sensitive to the exact amounts of ordinary matter and dark matter present in the early universe. The result was unequivocal. The beautiful, detailed maps from the Planck satellite, our most precise baby picture of the universe, showed that ordinary baryonic matter accounts for a mere 4.9% of the total mass and energy of the cosmos. Dark matter, the invisible substance required to form the gravitational scaffolding, makes up a staggering 26.8%. The rest, 68.3%, is an even more enigmatic substance called dark energy, responsible for the accelerating expansion of the universe. Here was confirmation from the dawn of time itself. Dark matter was not just an ad hoc solution to explain the spinning of galaxies. It was a fundamental and necessary ingredient of the Big Bang, without which the universe we know, with its magnificent galaxies and clusters, could never have formed at all. This cosmic fossil record had turned an astronomical puzzle into a cosmological certainty, and provided a new tool to map its presence across the heavens by observing its subtle gravitational effects on the very light that it so profoundly ignores. This cosmic fossil record had turned an astronomical puzzle into a cosmological certainty, and provided a new tool to map its presence across the heavens by observing its subtle gravitational effects on the very light that it so profoundly ignores. The blueprint for this extraordinary technique was not forged in an observatory, but in the mind of a single man, Albert Einstein. In 1916, he published his magnum opus, the General Theory of Relativity, which completely rewrote our understanding of gravity. For centuries, the universe had operated under the laws of Isaac Newton, where gravity was an invisible force, a mysterious action at a distance that reached out across the empty void to pull objects together. Einstein proposed a far more intimate and revolutionary idea. He declared that space and time are not a passive, empty stage upon which the cosmic drama unfolds, but are themselves dynamic players. They are woven together into a single, four-dimensional fabric called space-time, and the presence of mass and energy warps and curves this fabric. What we perceive as the force of gravity is simply the experience of moving along the contours and valleys of this curved space-time. A planet orbiting the sun is not being pulled by an invisible rope. It is following the straightest possible path through the curved space-time created by the sun's immense mass. In this new picture, even light, which has no mass, must follow these curves. A ray of starlight traveling through the universe is like a marble rolling across a stretched rubber sheet. If it passes near a heavy object, like a bowling ball placed on the sheet, its path will be deflected. This prediction, that gravity can bend light, was so profound that it offered the first real test of Einstein's radical new theory. The opportunity came in 1919 during a total solar eclipse. The English astronomer Sir Arthur Eddington led expeditions to the island of Príncipe off the coast of Africa and to Sobral in Brazil. Their mission was to photograph the field of stars surrounding the sun at the moment of totality, when the moon's shadow would block its brilliant glare. According to Einstein, the starlight passing near the sun's limb would be bent by its powerful gravity, causing the apparent positions of the stars to shift slightly. When Eddington and his team developed their photographic plates and compared them to images of the same star field taken months earlier, they found the tiny, predicted shifts. Einstein was right. Gravity bends light. It was our old friend, Fritz Zwicky, who first realized in the 1930s that this phenomenon could be used as a cosmic telescope. He reasoned that if a massive object like a galaxy, or even better, a whole cluster of galaxies, were to lie directly between us and a more distant light source, its gravitational field would act like a gigantic, albeit imperfect, lens. This gravitational lens could bend and focus the light from the background object, making it appear brighter, distorted, or even creating multiple images of it. For decades, this too was considered a mere theoretical curiosity. But with the advent of powerful modern telescopes, gravitational lensing has become one of the most vital tools in cosmology, allowing us to see the invisible by observing its gravitational signature. In its most dramatic form, known as strong lensing, a near-perfect alignment can smear the light of a distant galaxy into a beautiful, shimmering arc, or even a complete circle known as an Einstein ring. In other cases, it can produce multiple ghostly images of the same background object scattered around the foreground lens. By analyzing the geometry of these distortions, astronomers can precisely calculate the total mass of the lensing object, both the visible matter and the dark matter that is doing most of the gravitational work. More common and ultimately more powerful for mapping the universe is the subtle effect of weak lensing. In most cases, the distortions are far too slight to be seen by eye. A distant galaxy's shape might be stretched by less than 1%, but by observing millions of background galaxies across a vast patch of sky and using powerful computer algorithms to measure their subtle, collective alignment, like detecting a faint current in a vast ocean by observing the way it orients all the blades of seagrass, astronomers can build up a detailed map of the mass distribution in the foreground. This technique allows them to map the invisible scaffolding of dark matter across the cosmos, revealing the great filaments and voids that make up the universe's large-scale structure. And in 2006, this technique provided what many consider to be the smoking gun, the single most direct and powerful piece of evidence for the existence of dark matter. It came from a celestial object with the unpoetic name of 1E0657-56, better known as the Bullet Cluster. Located at a distance of about 1.6 billion parsecs, or 5.2 billion light-years from Earth, the Bullet Cluster is not a single entity, but the site of a colossal, ongoing cosmic collision. It is two entire clusters of galaxies that have smashed into each other at a staggering speed of 4,700 kilometers per second, which is nearly 10.5 million miles per hour. This cosmic cataclysm provided a perfect natural experiment to separate dark matter from ordinary matter. When the two clusters collided, their constituent parts behaved very differently. The galaxies themselves, which are mostly empty space, passed through each other like ghosts, their individual stars and planets barely noticing the encounter. The vast clouds of hot gas, the intergalactic medium that makes up the bulk of the ordinary matter in the clusters, did not fare so well. This gas, which is a superheated plasma, slammed into itself in a titanic shockwave, much like two tsunamis crashing together. The collision slowed the gas down, heating it to millions of degrees and causing it to emit brilliant X-rays, which were imaged by NASA's Chandra X-ray Observatory. The result was a stunning X-ray image showing the ordinary matter from both clusters lagging behind in the center of the collision, with one cloud shaped like a bullet, giving the cluster its name. The crucial question was, where was the gravity? If gravity was simply a modified property of the visible matter, as some alternative theories proposed, then the strongest gravitational pull should be centered on the hot gas, where most of the ordinary mass resided. But if dark matter was real, a non-interacting substance, then its vast halos should have passed right through each other, just like the galaxies. The dark matter should now be on the far sides of the collision, traveling along with the galaxies and far separated from the gas. Using weak gravitational lensing, astronomers mapped the total mass of the system. They meticulously analyzed the distorted shapes of tens of thousands of even more distant galaxies, whose light had passed through the colliding clusters. The result was breathtakingly clear. The lensing map revealed two giant, separate clumps where the mass, and therefore the gravity, was concentrated. These clumps were not in the center with the hot X-ray gas. Instead, they were located on the outskirts of the collision, perfectly matching the positions of the galaxies that had sailed through unimpeded. The dark matter had been physically separated from the ordinary matter. Gravity was not centered on where the visible atoms were. It was centered on where the invisible dark matter was. The bullet cluster was the incontrovertible proof. It was a snapshot of dark matter caught in the act, its existence written in the bent light of the distant universe. With this, the debate shifted decisively. It was no longer a question of if dark matter exists, but a far more profound and challenging question. What is it? Answering that question began, as it so often does in science, by first eliminating what it could not be. The most obvious hiding place for the missing mass was in ordinary, familiar matter that was simply dark. Perhaps the galactic halos were filled with countless dim objects, faint brown dwarf stars that never ignited, old, burnt-out neutron stars, or rogue planets cast adrift in the interstellar darkness. Maybe the mass was in primordial black holes forged in the Big Bang, or simply in vast, cold clouds of gas and dust that emitted no light. This collection of mundane but dark objects was given the collective name MACHOs, for massive, astrophysical, compact halo objects. For a time, this seemed like the most conservative and plausible solution. It required no new physics, only that our census of the cosmos was incomplete. And so, in the 1990s, several teams of astronomers set out to find them using a clever technique called gravitational microlensing. The idea was simple. If the halo of our Milky Way is full of these machos, one should occasionally pass in front of a distant star. Its gravity, though small, would act as a lens, briefly and characteristically brightening the background star's light. By monitoring millions of stars in nearby galaxies, like the Large and Small Magellanic Clouds, they hoped to catch these fleeting events, and from their frequency, calculate the total mass of the macho population. After years of patient observation, the results were definitive. Microlensing events were detected, but they were far too rare. Machos could account for, at most, a tiny fraction of the required halo mass. There simply were not enough of them. At the same time, another line of evidence from the early universe slammed the door on the idea of dark matter being made of any kind of normal, atom-based, or baryonic matter. The theory of Big Bang nucleosynthesis, which brilliantly predicts the observed primordial abundances of light elements like hydrogen, helium, and lithium, works only if the total amount of baryonic matter in the universe is tightly constrained to about 5% of the total cosmic density. If there were any more baryonic matter, the primordial fusion reactor of the early universe would have cooked the elements in different proportions than we observe today. The missing 27% had to be something else entirely. It had to be a new kind of matter, something not made of protons and neutrons, a substance that lay completely outside the otherwise triumphant standard model of particle physics. With the mundane suspects ruled out, physicists began to draw up a profile for this new cosmic particle. First and foremost, it had to be stable, or at least have a lifetime longer than the age of the universe. Otherwise, it would have decayed away by now. Second, it had to be dark, meaning it could not interact with electromagnetism, which is why it neither emits nor reflects light. Third, and most crucially, it had to be cold. This doesn't refer to its temperature, but to its speed. In the early universe, dark matter particles had to be moving slowly, sluggishly, so that their gravity could begin clumping together to form the small, dense seeds of the first galaxies. This rules out fast-moving or hot, dark matter candidates like the familiar neutrino, which, while dark and weakly interacting, zip through space at nearly the speed of light. A universe filled with hot, dark matter would have formed giant cosmic structures first that would then fragment downwards, a top-down scenario that does not match the observed bottom-up formation of galaxies we see today. So the culprit was a new, stable, non-baryonic, cold particle. And with this profile in hand, two primary suspects emerged from the world of theoretical physics. The first, and for a long time the leading candidate, was a class of particles known as IMPs, which stands for weakly interacting massive particles. The name is a perfect description. They are massive, hypothesized to weigh somewhere between 10 and 1,000 times the mass of a proton, which would explain their powerful gravitational influence. And they are weakly interacting, meaning they feel the force of gravity and the weak nuclear force, the same force that governs radioactive decay, but are immune to the electromagnetic and strong nuclear forces. This combination of properties makes them almost perfect ghosts, able to pass through solid matter as if it were not there. But the most compelling reason to believe in shrimps came from a stunning theoretical coincidence known as the WIMP miracle. To understand it, we must once again return to the fiery crucible of the very early universe. In the first moments after the Big Bang, the cosmos was so hot and dense that all kinds of exotic particles were being constantly created and destroyed in a frenzy of thermal equilibrium. WIMPs, if they exist, would have been part of this primordial soup, constantly being forged from pure energy and, in turn, annihilating each other when they met. As the universe expanded and cooled, the creation process slowed down. Eventually, a crucial moment arrived, known as freeze out. The universe became too sparse and the WIMPs too slow to find each other and annihilate. The annihilation stopped, and the remaining WIMPs were frozen into existence, becoming a permanent relic of the Big Bang. When physicists calculated the expected abundance of these relic particles, they found something remarkable. If you assume the particle has a mass on the scale expected from new particle physics theories, and that it interacts with the strength of the weak nuclear force, you get exactly the right amount of dark matter observed today, that crucial 27%. This apparent miracle suggested that dark matter was not some random cosmic accident, but was deeply and elegantly connected to the fundamental laws of particle physics. Even more beautifully, a popular and powerful theory called supersymmetry, or SUSY, naturally provided a perfect WIMP candidate. Supersymmetry was developed to solve some deep problems within the Standard Model, and it postulates that every known particle has a heavier, undiscovered superpartner. The superpartner of the electron is the selectron. The quark has the squark, and so on. The theory predicts that the lightest of all these new supersymmetric particles, most likely a mixture of superpartners of known neutral particles, called the neutralino, would be stable and would have all the properties of a WIMP. It seemed too good to be true. A new theory that solved problems in particle physics also handed physicists a perfect dark matter candidate whose abundance was a natural cosmological consequence. But the WIMP is not the only suspect. A second, very different and equally compelling candidate is a hypothetical particle called the axion. Unlike the WIMP, the axion was not invented to be dark matter. It was first proposed in the 1970s to solve a completely different puzzle within the Standard Model, known as the strong CP problem, which asks why the strong nuclear force, against all expectations, appears to obey a certain symmetry. The axion was the elegant theoretical fix. It was a new particle whose existence would naturally enforce this symmetry. It was named after a brand of laundry detergent because it cleaned up a messy problem in physics. It was only later that physicists realized that this problem-solving particle also had the perfect resume to be cold dark matter. Axions would be extraordinarily light, billions or even trillions of times less massive than an electron, and would interact with other matter even more feebly than WIMPs. But they would have been produced in colossal numbers in the early universe, not through thermal processes, but through the oscillations of a quantum field. They would form a vast, cold, coherent wave washing through the cosmos, behaving gravitationally just like a swarm of cold, heavy particles. So the stage was set. In one corner stood the WIMP, a heavyweight champion born from supersymmetry and blessed by the miracle of thermal freeze-out. In the other stood the Axion, a lightweight contender, an elegant solution to a deep-seated problem in fundamental physics. Both were plausible, both were well-motivated, but neither had ever been seen. With the suspects identified and the evidence for their existence overwhelming, the scientific community embarked on one of the most ambitious and challenging manhunts in the history of science. A global, multi-pronged effort to finally catch a particle of the dark. This global, multi-pronged effort to finally catch a particle of the dark began not by looking up at the heavens, but by journeying deep into the earth. The strategy, known as direct detection, is an exercise in listening for a whisper in a hurricane. It operates on a simple and profound premise. The Earth, in its orbit around the galactic center, is constantly plowing through the vast, invisible halo of dark matter that envelops our Milky Way. This creates a relentless, directional WIMP wind, a steady stream of dark matter particles passing through our planet, through our homes, and through our very bodies, every second of every day. The vast majority of these particles pass through without a trace, ethereal ghosts in the cosmic machine. But with almost unimaginable rarity, one of these WIMPs might, just might, interact directly with an atom of ordinary matter. The interaction is a game of cosmic billiards on a subatomic scale. A WIMP, traveling at hundreds of kilometers per second, strikes the dense nucleus of an atom, transferring a tiny amount of its momentum and causing the nucleus to recoil. The WIMP itself continues on its way, almost completely unaffected. But that recoiling nucleus is the signal, the telltale sign that a dark particle has passed by. The challenge is twofold. First, the energy of this recoil is minuscule, less than that of a single X-ray photon. Second, and far more daunting, is the fact that we live in a world awash with radiation. Our planet is constantly bombarded by a storm of high-energy cosmic rays from space, which create a shower of secondary particles that can perfectly mimic the signal of a WIMP. Furthermore, every substance on Earth, from the concrete in our buildings to the potassium in our bones, contains trace amounts of natural radioactivity. Each decaying atom releasing particles that create a cacophony of background noise. Detecting a WIMP on the Earth's surface would be like trying to hear a single pin drop in the middle of a continuous, deafening fireworks display. To hear that whisper, scientists had to find the quietest places on Earth, and those places are deep underground. Here, under more than a kilometer, or over half a mile, of solid rock, the relentless rain of cosmic rays is almost entirely absorbed, reducing the background noise by a factor of more than 1,000,000. And so, the great dark matter laboratories were built in the most unlikely of places, inside highway tunnels bored through mountains, and at the bottom of active mines. At the Gran Sasso National Laboratory in Italy, scientists drive their cars deep into the heart of the Apennine Mountains to reach their experiments. In Sudbury, Canada, physicists descend 2 kilometers, or 1.2 miles, into the earth in a rattling mine cage to reach SNOLAB, a state-of-the-art cleanroom facility carved out of a working nickel mine. And in Lead, South Dakota, the historic Homestake Gold Mine has been transformed into the Sanford Underground Research Facility, its deep shafts now home to the hunt for the universe's most elusive substance. In these subterranean halls, the quest for silence becomes an obsession. The laboratories are not just deep. They are fantastically clean. As any stray speck of dust could contain a radioactive atom that would spoil the experiment. The air is filtered, the walls are scrubbed, and the detectors themselves are constructed from materials that have been meticulously selected for their extreme radio purity. Every component, from the stainless steel vessels to the copper wiring and the solder on the circuit boards, is assayed for the faintest traces of uranium and thorium. The heart of the modern direct detection experiment is a vessel filled with a target material, a pristine collection of atomic nuclei waiting patiently to be struck. Over the years, many different materials have been used, but the leading technology now relies on one of the rarest of the noble gases, xenon. In experiments like the Large Underground Xenon, or LUX, detector, and its even larger successors, Xenon NT and LZ, hundreds or even thousands of kilograms of xenon are purified and liquefied inside a giant thermos-like vessel called a cryostat, cooled to a frigid temperature of around minus 100 degrees Celsius, which is about minus 148 degrees Fahrenheit. This vat of liquid xenon is the ultimate WIMP trap, and it is lined at the top and bottom with arrays of exquisitely sensitive light detectors called photomultiplier tubes. When a WIMP, or any other particle, interacts within this liquid, it produces 2 separate, crucial signals. The first is a tiny, immediate flash of ultraviolet light, a process called scintillation. This is signal 1, or S1, but the interaction also knocks a few electrons off the xenon atoms, a process called ionization. A strong electric field is applied across the detector, causing these freed electrons to drift upwards towards the top of the liquid. When they reach the surface, they are accelerated into a thin layer of xenon gas, where they generate a second, much brighter flash of light. This is signal 2, or S2. This two-signal system is the key to the experiment's power. The time delay between the first flash and the second tells the scientists the exact depth of the interaction within the detector. This allows them to ignore any events that happen near the walls of the container, which are more likely to be background noise. Even more importantly, the ratio of the amount of ionization to the amount of scintillation, the brightness of S2 compared to S1, is different for a recoiling nucleus than it is for a recoiling electron. Background radiation from gamma rays or beta decays almost always interacts with an atom's electrons. A WIMP, however, is expected to interact with the nucleus. By carefully measuring this ratio, scientists can powerfully discriminate between the golden nucleus recoiling signal they are looking for and the overwhelming background of electron recoils. For years, these incredible machines have listened in the deep, subterranean silence, growing ever larger, ever quieter, and ever more sensitive. And so far, what they have heard is a profound and deafening silence. Not a single unambiguous WIMP has been detected. Yet this is not failure. With each null result, with each year that passes in silence, the experiments are methodically closing the net. They are ruling out vast swaths of possible WIMP properties, telling theorists what dark matter is not. The simplest and most appealing models for WIMPs, those predicted by the most basic versions of supersymmetry, have now been almost completely excluded. The WIMP, if it exists, is proving to be even more elusive than first imagined. And so, the hunt continues, pressing forward into the unknown. The experiments get bigger, the xenon purer, the silence deeper, as humanity continues its extraordinary journey into the heart of the earth, patiently listening for a message from the dark. But while some scientists listened for a whisper from the cosmos, others decided to take a more forceful approach, to stop waiting for dark matter to come to them, and instead to try and forge it themselves in the most powerful machine ever built by human hands. This is the Large Hadron Collider, or LHC, a scientific instrument of truly monumental scale. It is a great ring, a particle racetrack 27 kilometers, or nearly 17 miles, in circumference, buried an average of 100 meters, or about 330 feet, beneath the picturesque Franco-Swiss countryside near Geneva. Operated by the European Organization for Nuclear Research, known as CERN, its purpose is singular: to recreate, for a fleeting instant, the unimaginable energy and density of the universe in the first trillionth of a second after the Big Bang. The guiding principle is the most famous equation in all of science, Albert Einstein's E equals mc squared, which reveals the profound and interchangeable relationship between energy and mass. In the quiet world of our everyday experience, mass appears solid and permanent. But in the extreme realm of high-energy physics, mass is a transient state, a form of condensed energy. The LHC is designed to be the ultimate conversion engine. By accelerating humble protons, the nuclei of hydrogen atoms, to incredible speeds and smashing them together, it transforms their kinetic energy into a brief, explosive fireball. A tiny pocket of the primordial universe from which new, heavy, and exotic particles can momentarily spring into existence before decaying back into more familiar forms. The journey of these protons begins in a simple bottle of hydrogen gas. They are stripped of their electrons and injected into a series of smaller precursor accelerators that boost their energy in stages. Finally, they are fed into the main ring. Here, in two parallel beam pipes maintained at an ultra-high vacuum, emptier than interplanetary space, the protons are whipped around the ring billions of times. Their path is guided by 1,232 massive superconducting dipole magnets, each one a marvel of engineering, cooled by liquid helium to a temperature of just 1.9 Kelvin, which is about minus 271 degrees Celsius or minus 456 degrees Fahrenheit, a temperature colder than that of deep space. At this temperature, the magnets can conduct enormous electrical currents without resistance, generating a magnetic field powerful enough to bend the path of protons traveling at 99.9999991% of the speed of light. At this incredible velocity, a single proton circles the entire 27-kilometer ring more than 11,000 times per second. Two beams of these protons, each containing hundreds of trillions of particles, are accelerated in opposite directions. Then, at 4 specific points around the ring, the beams are crossed, guided into a head-on collision at the heart of 4 colossal detectors. These detectors are the true cathedrals of modern science. 2 of them, Atlas and the compact muon solenoid, or CMS, are general-purpose experiments, as tall as 5-story buildings and weighing thousands of tons, packed with layer upon layer of sophisticated electronics. They are essentially gargantuan, 3-dimensional digital cameras designed to take a snapshot of the debris spewing out from the proton-proton collisions, which occur up to 1 billion times per second. The challenge for these detectors is to see the invisible, and this is where the search for dark matter at the LHC becomes a masterful piece of detective work. If WIMPs are created in a collision, they will, by their very nature, fly out of the detector without interacting with any of its components, leaving no track, no flash of light, no deposit of energy. They are ghosts in the machine. So how can they be found? The answer lies in one of the most fundamental laws of physics: the conservation of momentum. Before the collision, the two protons are moving in opposite directions with equal momentum. So the total momentum of the system in the plane perpendicular to the beams, the transverse plane, is 0. After the collision, the total momentum of all the newly created particles flying out must also add up to 0. The detectors are designed to meticulously measure the trajectory, energy, and momentum of every single visible particle that emerges from the collision. They add up all these vectors, performing a cosmic balancing act. If the final sum is 0, then everything has been accounted for. But if the sum shows a significant imbalance, if there is a large amount of momentum pushing in one direction with nothing to balance it on the other side, it is a powerful sign that something unseen has been created. Something massive and invisible must have shot out of the collision, carrying away momentum without leaving a trace. This signature is known as missing transverse energy, and it is the holy grail for dark matter hunters at the LHC. The most sought-after signal is what physicists call a mono-X event. In this scenario, the collision produces a pair of WIMPs which fly off undetected. But in the process, they recoil against a single high-energy visible particle. This particle could be a powerful jet of quarks and gluons, a single photon of light, or a Z boson. The detector would see a striking, unbalanced event. A single energetic jet or photon, and absolutely nothing on the opposite side. It is the perfect fingerprint of dark matter production. For more than a decade, the LHC has been smashing protons, and its vast global network of computers has been sifting through the petabytes of data from these collisions, searching for just such an imbalance. In 2012, this monumental effort led to the triumphant discovery of the Higgs boson, the particle that gives mass to all other fundamental particles, completing the Standard Model. But in the search for dark matter and the supersymmetry that was predicted to produce it, the result has been, once again, a profound silence. No convincing mono-X signals have been seen. No superpartners have emerged from the fireballs. The simplest, most elegant models of supersymmetry that predicted WIMPs at energies the LHC could easily access have been effectively ruled out. This silence, like the silence from the underground detectors, is not a failure, but a crucial piece of the puzzle. It tells us that the reality of dark matter is more subtle and complex than our simplest theories had hoped. Perhaps the particles are much heavier, requiring a more powerful collider to create them. Or perhaps they interact with ordinary matter through different forces, or in ways that produce more complicated, harder-to-see signatures. The null results from the LHC have forced physicists to cast a wider net, to think more creatively about the myriad ways the dark universe might connect to our own. And so, with the two most direct avenues for discovery yielding only a deeper mystery, a third great front in the hunt for dark matter opened up. one that looked not for the particle's arrival on Earth, nor for its creation in a machine, but for the faint, ghostly evidence of its self-destruction in the darkest depths of the cosmos. This search for self-destruction is rooted in a fundamental symmetry of nature, a cosmic echo of the WIMP miracle. The same physical processes that allowed pairs of WIMPs to annihilate each other in the dense heat of the early universe should still be at work today, albeit at a vastly reduced rate. In the cold, sparse expanse of the modern cosmos, dark matter particles are spread thin, and their encounters are rare. But they are not impossible. And in the places where gravity has gathered dark matter into its densest reservoirs, these fleeting encounters should be happening still, a slow, steady, and silent burn of cosmic annihilation. Each time two WIMPs meet and destroy each other, they should convert their mass into a shower of energetic, visible particles from the standard model. The exact byproducts depend on the specific theoretical model, but the most common and sought-after signal is a spray of the most energetic form of light in the universe, gamma rays. These gamma rays are the key because, unlike charged particles such as electrons or positrons, their paths are not bent by galactic magnetic fields. They travel in a perfectly straight line from the point of annihilation to our telescopes, acting as unambiguous pointers to their source. The strategy of this indirect detection is therefore to scan the heavens for a telltale excess of gamma rays, a faint glow emanating from regions where dark matter is expected to be most concentrated. The prime targets are the great gravitational wells of the cosmos. First and foremost is the very center of our own Milky Way galaxy, a chaotic and brilliant region where the gravitational pull is strongest, and the density of the dark matter halo is predicted to reach its peak. Another promising hunting ground is the population of dwarf spheroidal galaxies that orbit the Milky Way. These small, faint satellites are the most dark matter-dominated objects known, with 1,000 times more mass in dark matter than in stars. Their lack of conventional astrophysical activity, like star formation or energetic pulsars, makes them exceptionally clean targets, where any gamma ray signal would be harder to explain away. To see this faint, high-energy light, humanity built a new eye in the sky. In 2008, NASA launched the Fermi Gamma Ray Space Telescope into a low Earth orbit, circling the planet at an altitude of 565 kilometers, or about 351 miles. Fermi is not a telescope in the traditional sense, with mirrors and lenses. It is a particle detector, a sophisticated instrument designed to capture gamma rays, which are so energetic they pass right through conventional mirrors. When a gamma ray enters Fermi's main instrument, the Large Area Telescope, it strikes a thin sheet of tungsten, a dense metal. The interaction converts the single photon of light into a pair of particles, an electron and its antimatter counterpart, a positron. These two particles then fly through a series of silicon strip trackers, which record their trajectories, before slamming into a calorimeter that measures their total energy. By reconstructing the paths of this electron-positron pair, scientists can trace their origin back to a single point on the sky, determining the direction and energy of the original gamma ray with remarkable precision. Over years of operation, Fermi has meticulously scanned the entire sky again and again, building up the deepest and sharpest map of the gamma ray universe ever created. And when astronomers pointed it towards the center of our galaxy, they found something tantalizing. After carefully modeling and subtracting all the known sources of gamma rays, the emissions from the supermassive black hole at the galaxy's heart, the light from thousands of individual pulsars, and the diffuse glow created when high-energy cosmic rays collide with interstellar gas, a mysterious excess remained. It was a faint but persistent spherical haze of gamma rays, extending out from the galactic center for about 5,000 light years. What caused a thrill of excitement to ripple through the physics community was that this signal matched the predictions for dark matter annihilation almost perfectly. The energy of the gamma rays, peaking at a few giga-electron volts, was consistent with the annihilation of a WIMP with a mass between 30 and 100 times that of a proton. The spherical shape of the glow, or its morphology, was exactly what was expected from a dense central cusp of a dark matter halo. For a while, it seemed that this could be it, the first credible, indirect sighting of our universe's missing mass. But the galactic center is the most complex and poorly understood region of our galaxy, a cosmic metropolis filled with exotic objects and violent processes. And an alternative, more mundane explanation soon emerged. The culprit could be a large, previously unknown population of ancient stars called millisecond pulsars. These are the incredibly dense, burnt-out cores of massive stars, neutron stars that have been spun up by a companion star until they are rotating hundreds of times per second. They are known to be powerful gamma-ray emitters. And if thousands of them were concentrated in the galactic center, too faint and numerous to be resolved individually by Fermi, their combined light could create a diffuse glow that perfectly mimics the expected dark matter signal. The debate has raged for years, with sophisticated statistical analyses of the Fermi data attempting to distinguish between the smooth glow expected from dark matter and the more grainy or point-like texture that would be produced by a multitude of unresolved pulsars. While no final consensus has been reached, the evidence has been slowly tilting in favor of the pulsars. Other searches, using different messengers, have yielded similarly ambiguous results. The alpha magnetic spectrometer, a 7.5-ton particle detector mounted on the International Space Station, has measured an unexpected excess of high-energy positrons, but these too could be explained by nearby pulsars. Deep in the Antarctic ice, the Ice Cube Neutrino Observatory, a colossal detector that uses a cubic kilometer, or about 0.24 cubic miles, of pristine ice to look for high-energy neutrinos, has searched for signals from WIMPs captured and annihilating in the core of the Sun, but has so far found nothing. The path of indirect detection, like those of direct detection and collider production, has led to a landscape of tantalizing hints and frustrating dead ends. The profound silence from the universe has been deafening. The failure of these three great experimental fronts to find any definitive sign of a WIMP has forced a period of deep reflection and has given new life to a radical minority view. Perhaps the problem is not that our telescopes are blind to a missing particle, but that our understanding of gravity itself is flawed. The failure of these three great experimental fronts to find any definitive sign of a WIMP has forced a period of deep reflection and has given new life to a radical minority view. Perhaps the problem is not that our telescopes are blind to a missing particle, but that our understanding of gravity itself is flawed. This idea, to question a law of nature that has stood firm for more than 3 centuries, is the ultimate in scientific heresy. And yet, it was precisely this question that was asked in the early 1980s by an Israeli physicist named Mordechai Milgram. At the time, he was working at the Weizmann Institute of Science, contemplating the very same flat galaxy rotation curves that Vera Rubin had so brilliantly measured. While the rest of the world was busy speculating about the nature of the missing matter required to explain them, Milgram took a step back and considered a different possibility. What if there was no missing matter at all? What if the equations of gravity, as written down by Isaac Newton, were simply an approximation, a law that works perfectly in the high-gravity environment of our own solar system, but breaks down in the incredibly weak gravitational fields in the outer fringes of a galaxy? He proposed a bold modification to Newton's second law, the famous equation that states force equals mass times acceleration. Milgram suggested that this relationship was not linear. He introduced a new fundamental constant of nature, a critical acceleration scale, which he called a knot. This constant represents a threshold. In environments where the gravitational acceleration is high, far above this A0 threshold, like it is for the Earth orbiting the Sun, or for an apple falling from a tree, gravity behaves exactly as Newton described. Its force diminishes with the square of the distance. But in regions of extremely low acceleration, far below the A0 threshold, Milgram proposed that gravity behaves differently. It becomes inherently stronger than Newton's law would predict. Its grip fades more slowly, diminishing in direct proportion to distance, not the square of the distance. the value of this A0 constant is incredibly small, about 100 billion times weaker than the gravitational acceleration we feel on the surface of the Earth. Such feeble accelerations are never encountered anywhere in our solar system, which is why we would never have noticed this deviation. But for a star on the outer edge of a galaxy, orbiting the distant center once every few 100 million years, its acceleration is squarely in this ultra-low regime. In this realm, Milgram's theory, which he called modified Newtonian dynamics, or MOND, makes a startling prediction. The stronger, modified gravity is all that is needed to hold the fast-moving outer stars in their orbits. No dark matter is required. For many years, MOND was largely ignored by the mainstream physics community, considered a clever but ultimately niche idea. Yet it refused to go away, primarily because of its stunning and persistent success at explaining the behavior of galaxies. MOND didn't just qualitatively explain why rotation curves were flat. It quantitatively predicted their exact shape from the visible matter alone. Give a MOND theorist a map of a galaxy's stars and gas, and they could predict its rotation curve with uncanny precision, often better than a dark matter model, which has the extra freedom of allowing the theorist to adjust the size and shape of the invisible halo to fit the data. Furthermore, MOND provided a natural and elegant explanation for a puzzling astronomical observation known as the baryonic Tully-Fisher relation. This is a remarkably tight empirical law which states that a galaxy's total brightness, which is a proxy for its total mass in ordinary baryonic matter, is directly proportional to the fourth power of its rotation speed. In the standard dark matter model, this relationship is something of a mystery. It's an emergent property that comes out of complex simulations, but it's not obvious why a galaxy's visible matter should be so tightly tethered to the rotation speed dictated by its dark matter halo. In MOND, however, this relationship is a core prediction. It falls directly out of the fundamental equations. The theory's ability to predict this galactic law so effortlessly is perhaps its most compelling piece of evidence. Despite these remarkable successes on the scale of individual galaxies, MOND has failed to dislodge the dark matter paradigm. Because as we zoom out to larger cosmic scales, the theory begins to falter badly. Its biggest problem lies where the dark matter story began, in clusters of galaxies. When Fritz Zwicky first observed the Coma cluster, he found that the visible matter was outweighed by the unseen mass by a factor of hundreds. When MO is applied to galaxy clusters, it does reduce the discrepancy, but it doesn't eliminate it. The modified gravity of MOND can only account for about half of the required gravitational pull. Even a MOND supporter is forced to concede that there is still a significant amount of missing mass in clusters, often speculating that it could be in the form of massive neutrinos or some other, less exotic form of dark matter, which significantly weakens the theory's central claim of eliminating the need for unseen particles. And then there is the bullet cluster, this cosmic collision where the gravitational mass was shown to be physically separated from the hot baryonic gas, remains Mond's greatest stumbling block. Mond is a theory of modified gravity that is sourced by ordinary matter. The gravity should be strongest where the atoms are. Yet the lensing data from the bullet cluster clearly shows that the center of gravity is not with the gas in the middle, but with the collisionless components on the sides. This observation is almost impossible to explain with Mond alone, and provides powerful, direct evidence for a collisionless, non-baryonic form of matter. The final, and perhaps most insurmountable hurdle for Mond is the cosmic microwave background. The beautiful and intricate pattern of hot and cold spots in the CMB is explained with exquisite precision by the standard cosmological model, which includes both cold dark matter and dark energy. The relative heights of the peaks in the CMB's power spectrum are a direct measure of the cosmic recipe, and they demand the existence of non-baryonic dark matter that could begin to clump gravitationally long before ordinary matter was free to do so. Manda, in its basic form, has no mechanism to replicate this success. It struggles to explain how cosmic structures grew so quickly in the early universe without the initial gravitational scaffolding provided by dark matter. This has left MOND in a precarious and fascinating position. It is a theory that works almost magically well on the scales it was designed for, but which fails dramatically on the larger cosmological scales where the evidence for dark matter is most robust. For its supporters, MOND is a sign that we are missing a fundamental piece of our understanding of gravity. For its detractors, it is merely a clever mathematical fit, a coincidence that masks our ignorance of the complex ways that dark matter and ordinary matter interact. Whatever its ultimate fate, MOND has served as a vital intellectual gadfly, a constant and necessary reminder that the case is not completely closed, and that in the quest to understand the universe's hidden architecture, no assumption, not even the law of gravity itself, should be beyond question. And so our story arrives at a place of profound and tantalizing uncertainty, a great crossroads in 21st century physics. In one direction lies the path of a missing particle, a new and fundamental component of the cosmos, still stubbornly hiding just beyond the reach of our most ingenious experiments. In the other lies the path of a missing piece of physics, the unsettling notion that our most cherished law of gravity is incomplete. Our journey to this point has been a century-long epic of scientific discovery. It began not with a bang, but with a whisper. In the meticulous star charts of Jacobus Captain, who first noticed a subtle gravitational ghost in the motions of our own galactic neighborhood. That whisper became an audacious shout in the 1930s, when the irascible Fritz Zwicky saw galaxies in the Coma cluster moving with such impossible speed that they required a vast, unseen scaffold of dunkel materie to hold them together. For decades, this idea languished in obscurity until the patient, persistent work of Vera Rubin in the 1970s made the problem undeniable, revealing that every spiral galaxy she looked at was spinning far too fast, held in the grip of an enormous, invisible halo. The evidence then moved from the galactic to the cosmic, confirmed by the most ancient light in the universe, the faint afterglow of the Big Bang, whose detailed pattern served as a cosmic decree, a recipe for the universe that declared unseen cold dark matter to be more than 5 times as plentiful as all the atoms we can see. We learned to map this invisible substance by its gravitational influence on light, a technique that culminated in the spectacular image of the bullet cluster, a cosmic collision that provided incontrovertible proof, separating the dark matter from the ordinary matter and showing beyond doubt where the gravity truly resides. With the existence of dark matter firmly established, the great hunt began. We have traveled to the quietest places on Earth, descending into deep subterranean mines to listen in shielded vats of noble liquids for the faint recoil of a single atom struck by a wimp. A search that has so far been met with only a profound silence. We have built the most powerful machine in history, the Large Hadron Collider, to smash protons together in fiery collisions, hoping to forge a particle of the dark from pure energy. Yet no new ghosts have emerged from the machine. And we have looked to the heavens with gamma-ray eyes, searching for the faint signal of dark matter annihilating itself in the dense core of our galaxy, only to find ambiguous whispers that could just as easily be the chorus of 1,000 undiscovered stars. This great impasse, this frustrating and beautiful mystery, has left us to wonder. Is it possible we have been chasing a phantom? That the universe is playing a far more subtle game, one where the laws of physics themselves are different on the grandest scales? The story of dark matter is therefore far from over. In many ways, it has just begun. The overwhelming evidence tells us that the universe we see is but a sliver of the whole, a 5% glimmer on the surface of a vast, dark ocean. The quest to understand the hidden 95% has reshaped our understanding of cosmic history, from the formation of the first stars to the intricate dance of galaxies. It is a testament to the power of human curiosity, our collective refusal to accept the universe at face value. Whether the final answer is a new particle, a new force, or a new understanding of gravity, its discovery will undoubtedly begin the next great chapter in our exploration of the cosmos. For in the quest to illuminate the dark, we are ultimately charting the true and astonishing extent of the cosmos and our own place within it.